For years, interacting with AI meant sending isolated queries to stateless interfaces, but the architecture of automation has evolved. We are now deploying stateful, persistent cognitive entities capable of executing complex, long-horizon tasks. Most commercial chatbots attempt to govern these new entities by cramming identity, formatting rules, and session context into a single, massive system prompt. In a sustained, multi-turn interaction, the conversation history rapidly accumulates. The active token buffer fills, stretching that monolithic prompt to its maximum mathematical capacity. The result is severe behavioral degradation. The agent suffers intent drift, losing track of parameters and hallucinating operational boundaries. To make room for new conversational data within strict context limits, the reasoning model silently drops its earliest instructions, which usually contain its core identity. OpenClaw addresses this degradation by decentralizing the system prompt into a file-first identity management system. At the center of this ecosystem is the soul.md file. It acts as the agent's unalterable behavioral core and the absolute arbiter of its trust boundaries. An agent cannot remain hallucination-resistant if its persona is constantly overwritten by chat logs. Stability requires permanently separating the entity's philosophical identity from its transient memory. OpenClaw enforces this by isolating core data into specialized workspace markdown files. Soul.md serves as the manifesto, strictly dictating who the agent is. In parallel, agents.md is the operational manual, dictating what the agent must do. Finally, memory.md handles persistent state and curated facts. Because these elements live in entirely isolated physical files, the reasoning model never conflates its underlying persona with its daily operational workflow instructions. This isolation enables robust multi-agent topologies. A single gateway process runs multiple agents simultaneously, making cross-contamination structurally impossible. A highly formal work orchestrator and a casual home assistant can operate side by side, each governed by its own uniquely authored soul.md file, completely unaware of the other. By decentralizing instructions into purpose-built documents, OpenClaw replaces a fragile single point of failure prompt with a hardened, immutable control plane. To maintain the integrity of this control plane, OpenClaw enforces a rigid mechanical protocol at the genesis of every new conversational session. The session boot sequence forces the agent to physically read its workspace files from the disk before generating output. Injecting the soul and memory logs deliberately costs 4,000 to 10,000 tokens upfront. This prevents cold starts, guaranteeing strict adherence to the persona. However, during heavy engineering tasks, this front-loaded context, combined with deep conversational history, threatens to saturate the active window. To mitigate this, OpenClaw implements a pre-compression memory flush. As the buffer nears its maximum mathematical threshold, the gateway inserts an invisible system trigger. A compression algorithm aggressively drops early chat history to save space. Crucially, the system structurally pins the soul.md file at the top of the context. Even as the agent experiences transient amnesia regarding older turns, its core identity remains firmly anchored. Repeatedly paying the token tax to re-inject these core files is the only mechanical method to guarantee an autonomous agent survives context compaction. The internal anatomy of a perfectly constructed soul.md file is rigidly divided into 4 sections. The first is core truths. This section does not outline specific step-by-step workflows. It provides the overarching philosophical heuristics the agent must use to navigate ambiguity and edge cases. The paramount instruction housed here is the Learn First protocol. If the agent encounters an unknown software variable or a missing dependency, its primary instinct must be to spawn local web search tools and parse execution logs before it is allowed to ask the human operator a question. The instructions must also authorize the agent to hold technical opinions. If it ingests a deeply flawed deployment script, it is programmed to state the flaws directly and bluntly, rather than blindly attempting execution. This requires an explicit action bias. The model must default to drafting actual code blocks and running diagnostic scripts, instead of acting as a passive chatbot that merely summarizes its intent to do so later. Instilling aggressive resourcefulness into the core truths ensures the agent operates as an independent engineering partner, preventing it from devolving into a helpless query relayer. While the core truths dictate what the agent should consider, Section 2, Boundaries, explicitly defines the hard limits of what the agent cannot do. This section functions as the operational immune system, protecting both the host machine and the agent's own cognitive self-preservation. Internally, the agent must be explicitly forbidden from executing infinite loops or altering its own core configuration files within the active session. If the environment grants the agent local shell or bash access, these boundaries must implement a strict production lock protocol. Under this lock, the autonomous modification of global packages or the execution of destructive file system operations is entirely blocked without explicit textual confirmation from the user. Boundaries must also gate external communications. The agent is authorized to compile data and draft messaging payloads, but it must never transmit that data to public internet surfaces unreviewed. Establishing absolute, unbypassable security invariance is the only safe method for granting a reasoning model local execution autonomy over a host machine. The final structural pillars that govern output are Section 3, Vibe, and Section 4, Continuity. Base language models are pre-trained to be overly apologetic and subservient. The Vibe section must deliberately eradicate these performative customer support behaviors. Vague instructions force the neural network to sample across a massive, inefficient probability distribution. Instead, utilizing explicit negative constraints, like never begin with an apology, creates hard syntactical walls. This instantly collapses the probabilistic output space, forcing the system to default to tight deterministic formatting. The continuity section manages the agent's temporal state, which exposes its single largest attack surface, memory poisoning through indirect prompt injection. If an agent is allowed to autonomously scrape untrusted web data, an attacker can embed malicious logic on a web page that tricks the agent into writing a new, restrictive rule directly into its persistent memory files. The primary defense against this cognitive subversion is a human-in-the-loop proposal merge. The continuity rules force the agent to draft any self-modification into a separate proposal document, requiring cryptographic approval before the core state files can be altered. Combining mathematical rigidity of negative constraints with strict file-level drift guards ensures the agent's identity survives the inherent risks of its own operational autonomy. When these core elements are properly aligned within a completely isolated physical workspace, the system achieves true stability. In this architecture, the soul.md file serves as the agent's immutable control plane. Enforcing negative constraints and isolated operations creates a stable, repeatable operational envelope over long durations. To study community-tested configuration templates or to explore the deployment of advanced multi-agent routing topologies, join the architects at OpenClaw Toronto via openclawtoronto.com.